Hello and welcome to NCC Group's Cryptopals Guided Tour. My name is Eli, I'll be your guide. In this video, we'll be wrapping up Set 2 by taking a look at Challenge 16, which deals with CBC bit-flipping attacks. Now this is a really good challenge. It's a strong attack on CBC mode, and in what's becoming sort of a recurring theme, this is yet another chosen ciphertext attack, meaning that it only really applies to unauthenticated CBC, but honestly, the Venn diagram between people who still like CBC in 2022 and people who still forget to MAC their ciphertexts in 2022, well, it turns out to have a lot of overlap. So this is a good attack to know. A similar attack exists on unauthenticated counter mode, and we'll get to that in Set 4, but for now, let's focus on CBC mode. And on this challenge in particular, which has us forging an admin token, much like in Challenge 13, but this time we get to control a user data string in the middle of the plaintext, and that's the only direct influence that we have on said plaintext. The Oracle is going to quote special characters, so we can't embed the admin flag directly into our user data. Instead, we're going to have to figure out how to use CBC bit flipping to rewrite this user data string after it has already been encrypted. This might not sound like something that should be possible, and I agree it shouldn't be possible, but nevertheless it is. And this is the type of thing that you're risking if you don't use authenticated encryption. How bad is it? Well, let's take a look. So we'll start out here on familiar ground. This is CBC mode encryption with a null message. And if we flip some of the arrows around, we'll get CBC decryption, which should look familiar as well. And you might recall from our earlier discussion that in CBC decryption, each plaintext block depends on exactly two ciphertext blocks, as you can see here. The lower of these two ciphertext blocks gets run through the cipher, and then the upper ciphertext block gets XORed against the result of that decryption. Now suppose we XOR some arbitrary buffer into this ciphertext block. This change will propagate through the XOR and into this plaintext block. And because XOR is associative, the result is that the plaintext will change by the exact same XOR differential as the ciphertext did. This is a very useful and powerful property of CBC mode, at least useful for attackers. There is a slight catch though, which is that this change also propagates here through this decryption operation, which in effect scrambles this block. So the probability of this attack being detected depends entirely on how important and how closely checked the contents of this block are. So now let's put this into context. For this challenge, there are two functions that we have access to. The first function takes user input, escapes any instances of semicolons or equal signs, which are the meta characters here, and then it sticks some structured text onto the start and end of our string and encrypts the result under a secret key and returns the ciphertext. The second function here takes a ciphertext, decrypts it, assumes that it's structured in the same way as the prefix and postfix, and consequently splits it on semicolon characters, then treats each split field as a two-tuple representing a key value pair, and checks for a tuple identifying the user as an admin, or, equivalently modulo error cases, it could just do a substring search for the string semicolon admin equals true semicolon, and that works too, and that's what we'll do in our implementation. Now, the challenge is forge an admin token that this second function accepts. As we just saw, we can't pass the admin token directly because it'll get escaped. One weakness that we do see, though, is that the second function has no integrity checks for its ciphertexts, which means that chosen ciphertext attacks, like the bit-flipping attack we just saw, are in play. So let's try to set things up for that. We'll start by passing in a two-block user data string and trying to keep all our changes confined to those two plaintext blocks. Conveniently, the prefix is exactly 2 blocks long, leaving our user data perfectly aligned with the block boundaries. If this wasn't the case, we could always prepend padding bytes, but in this case, we don't even need to do that. So now we have a perfect setup. Recall that for this or any input, what we get back from the first function is the CBC ciphertext for this plaintext buffer. In practice, this ciphertext buffer might have the IV prepended, but that's an implementation detail, so we'll ignore it here and focus on the actual ciphertext. So after we get this buffer ciphertext, we'll modify its third block, which corresponds to our first attacker-controlled plaintext block. And just for example, if we XOR OXAA into the ciphertext here, look what happens to the plaintext. It scrambles the first block, but it nulls out the second one. Now, of course, we're in the home stretch. We can combine this nulling mask with a second XOR mask that has whatever contents we want. And again, through the associative property of XOR, these same contents will show up in the plaintext. So this change results in a plaintext which does contain some junk bytes, but it also contains the admin string, which is all that our validator is looking for. And of course, if the junk bytes are a problem, then as long as we can get the first function to rotate its key, we can repeat this process until those bytes all fall within the printable ASCII range minus meta characters. Of course, this will take a while. Since ASCII is a 7-bit encoding, and most ASCII values are printable, this condition is met for each byte with a probability of just under 2 to the negative 1. So the joint probability for the entire block meeting the condition will be just under 2 to the negative 16. In fact, if we want to get precise, constraining ourselves to allowed printable characters, our probability of getting a printable junk block ends up being a little closer to 2 to the negative 22, or about 1 in 10 million, which might sound small, but in cryptography, you take those odds. If trials are cheap, then this is very exploitable. And heck, even if trials are expensive, at a few trials per second, the search would complete in less than a month on average, which is not fast, but it's very far from impossible. Anyway, this step isn't really required for the problem description, but it's something that could easily come up when exploiting this vulnerability in practice. It often comes up with similar attacks as well, so I just thought we'd take some time to touch on it. But speaking of practice, let's switch gears and write some code. All right, and here we are. As we recall, our problem statement is right here. We have this prefix and this suffix, and we are quoting out semicolon and equals sign. And in spite of that, we need to get this string with semicolons and an equals sign into the middle of our token. And we have two different ways of implementing this. One of them is gratuitously complex, and one of them is gratuitously straightforward. So you can guess which one we're going to use. So let's get to it. We'll start out with some things that we know we're going to need. As always, 32 byte keys, not strictly necessary, but they make me feel good. And sometimes that's enough. We actually can see if we go to the definition for AES here that it supports 16, 24, or 32 byte keys. So this is the most conservative of those choices. All of them are obviously more than fine, but this is the one that I like to use given the choice. There's the too much crypto school of thought, and there's the not enough crypto school of thought. I personally say, damn performance, give me security margins. That's just me, though. Oh, and then I guess we're going to need, so this is our random AES key, and we only need one key. This does not need to be regenerated, so we're not putting this in a closure or anything. We're just prefixing it with an underscore to say, hey, don't look at this, don't cheat. And we're also generating the IV here. Ordinarily, this will be really bad because you don't want a static IV, but in this case, we're only going to make one encryption. And also, it's convenient to have the IV in a global scope because we want it to be accessible to both of our functions, for the encryption function and the decryption function. And we could do that by returning it from the encryption function and passing it into the decryption, or we could just make it visible to them. And so I'm just going to choose a tiny bit of laziness today and do it this way. And I believe that's the URL encoding for a semicolon. I'll probably check that in my browser in some clever way, but I'm not going to bother. Yeah, let me see. Let me just... Yep, that's 3D. And semicolon is right above it at 3B. Don't ask me how I remember these things. I really couldn't tell you. And there we go. And yeah, like I said, we could generate the IV right above this and then return it from this, but that's just a whole lot of data shuffling and bookkeeping that I'm not interested in doing. And I'm going to add a quiet parameter onto this check for admin function, just because I feel like for troubleshooting, it might be useful to be able to see what the plain text is after decryption. If we accidentally XOR the wrong thing in and the test doesn't pass, we want to see why it doesn't pass, right? So let's have that option there. Oh, and this will return a Boolean. And by now you should easily recognize this whole rigmarole. And there we go. These are the two functions that we need in order to start the attack. So now let's do the actual attack. And this will generate out of thin air a admin token. We'll start by passing a couple blocks of constant bytes, and we're just going to use a printable value for this. Any as good as another. I'll just use A. And I like A for a couple of reasons. It's traditional, and it also allows me to name this variable A block, which, I don't know. Maybe that's not funny, but it is to me. And so we want to define an XOR mask that we will XOR into the ciphertext block corresponding to the second block of our data within the plain text. And this is going to be that mask. And if we just set this equal to the A block, then it will zero out the corresponding plain text. So instead, let's set it equal to the XOR. Of the A block with this desired string. And I'm going to write justify this within the block. I guess I should write. But yeah, so justify this out to the block size and then pad it with A bytes. That will actually null out the preceding bytes in the flipper so that the corresponding bytes will be left at value A in the resulting plain text, which is what we want because A bytes are printable and null bytes are not. So this just is slightly more likely to avoid causing an error or tripping an alarm. Might just look a little bit less conspicuous, hopefully. It's not the sort of thing we actually have to worry about in this toy context, but in the real world we might. So there you go. And we're just going to take this flipper block and orient it so it's the fourth block in the plain text. The reason for that is that we know that this is 2 blocks long, and then we're going to have 1 block of A's that's going to get scrambled by this attack. And so that's these 3 blocks that need to be accounted for. And so we're going to take our flipper and add, basically 3 blocks of null bytes before it. And I just think this is a more legible way of doing that. And then we're going to left justify it to the length of the ciphertext. And we're also going to put null bytes after it. This is just for convenience because it allows us to do this. Now we can XOR these together because they have equal length. And I believe that writing this like this will cause this to be printed out before this. And let's find out if I'm right about that. I am indeed. And here we go. This is the result. Our ciphertext is obviously total nonsense, but we can see that when it gets decrypted, we end up with 1 block of total nonsense and then a little bit of screaming. And then admin equals true, followed by comment 2 equals like a pound of bacon, which, if you were wondering, is how we're cooking MCs. So there you go. That's challenge 16. That rounds out set 2. I hope you enjoyed this. I hope maybe you found it helpful or interesting. And I hope you'll join me for set 3 and the rest of the challenges. Thanks for watching. Have a great day.